non-commutative geometry. So it gives you a non-commutative analog of Milners monodromy map in differential topology. Okay, so I'm going to give you some motivation for the construction that I'm going to make, and then at the end, I am going to make, toward the end of the lecture, I am going to make some conjectures about the multivariate operator theory construction that I make, and then verify some of those conjectures in some toy models. So the setup, the basic setup is exactly the same as the previous talk. So the fundamental concept is that of a Hilbert A module. Capital A is going to always denote the ring of polynomials with complex coefficient in m variables. Whenever you see I is going to be an arbitrary ideal of the polynomial ring. So a Hilbert A module is just a Hilbert space together with the ring homomorphisms from ring of polynomials to the ring of, let's say, bounded operators on a Hilbert space. Our Hilbert spaces are always infinite dimensional and separable. Mm-hmm. So the data in a Hilbert A module is exactly this one. Is a Hilbert space together with a commuting tuple of bounded operators on it. So that's just a Hilbert space. So the fundamental example is, let's say, the Bergman space on a domain. The multiplication operators is the module operation is given by multiplication of polynomials. Mm-hmm. And okay, a more interesting example, it comes from the quotient of, for example, Bergman spaces with closure of ideals. So here, the module operation is just multiplication by polynomials followed by orthogonal projection into Iperb. Mm-hmm. So in other words, Toeplitz operators. So for some reasons, instead of the Bergman space, you can use any other analytic Hilbert spaces of analytic functions. For example, in this talk, for no good reason, just because it's more convenient. So we are going to use the Rory-Arbison space, and it's quotient by closure of ideas. So the Rory-Arbison space is a Hilbert space of analytic functions with the reproducing kernel given by this guy over here. Mm-hmm. So, but you can equally use Bergman spaces. So we are gonna give so that was the idea of Arbison and Douglas, to give some non-commutative analog of classical algebraic geometry. So these algebraic geometers showed how to do geometry by studying the coordinate ring of ideals. So more specifically, they discovered this one. This is one of their discoveries, basically due to Hilbert. So he showed that there is more or less a one-to-one correspondence between ideals of the polynomial rings and affine subvarieties of CN, or closed subschemes in the language of Grothendieck. So now we are gonna, so the correspondence is given by, okay, the link between these two objects, algebraic object and these geometric objects, is the coordinate ring. And here is an idea, is a...
wait a minute. Can you give a simple example of very simple, say, A of two variables, some ideal A, what subvariety V will you have, and C2?
Right. For example, right, if your ideal is generated by coordinate functions Z1, right? If your variety is given by, no, if your ideal is the ideal generated by Z1 coordinate function, right? Okay. So then by affine subvariety, V is the affine variety given by zero sets of Z1, which is a complex hypersurface, Z1 equal to 0. So that's what I mean by the correspondence between ideals and affine subvarieties. So you send an ideal I to the set of points in CM such that all which are 0, which are killed by every polynomial P in I. Right? And in the other direction, if you have a affine subvariety V, a set of points given by 0 set of polynomials, the ideal I is given by the set of all polynomials which are 0 at every point of your variety V. That is Hartshorne first chapter. Okay, but now, okay, the link, the most important thing is this one over here, coordinate ring. For example, Hilbert, to study the intersection of two varieties V and W, if V and W are two algebraic varieties, to study the intersection of V and W and to prove the Bezos theorem, right? In a classical algebraic geometry. So Hilbert resolve A quotient the ideal defined by V plus the ideal defined by W. So if you want to study the intersection of two varieties, go and define, define the ideal of V, add it with the ideal of W, and study its coordinate ring. That gives you an algebraic way to define intersection multiplicities. And then, because the most difficulty in proving this Bezos theorem, for example, in classical algebraic geometry, was to define intersection multiplicity. And that's how van der Waerden and Hilbert found a way to define this intersection multiplicity and state the Bezos theorem in this full generality and prove it. Okay, but this is a fundamental idea of algebraic geometry. And okay, now we are gonna use Toeplitz operator to imitate this process of coordinate ring, the construction of coordinate ring. So the coordinate ring is given by the quotient of your ring of polynomials mowed out by your ideal. But you have a similar construction here that we are going to use that. So an operator theory replacement for the classical coordinate ring in algebraic geometry is this one over here. So you choose your favorite Hilbert space of analytic functions. So I have used the de Rorey-Arveson space. You can use the Bergman space, for example, and then mode it out by the closure of your ideal. And so consider it as a Hilbert module over A. So it's not a ring anymore like before. So in algebraic geometry, A over I is a ring, but here it's not a ring anymore because multiplication, okay. But it's a Hilbert A module. At least you can multiply an element here in Iperb, right, by a polynomial and then do orthogonal projection. So that's Iperb, a Hilbert modular structure over the ring of polynomials. So let's see if we can find. So the work of Arveson and Douglas showed that you can extract some geometrical information from this multivariate operator theory object Iperb. So this is Iperb. So as a Hilbert space, so it's clear what is it, right? It is the set of all analytic functions in the de Rorey-Arveson space which are orthogonal to I, to every element in I. But it also has a Hilbert modular structure. The Hilbert modular structure is given by Toeplitz operator. So it's like, right, so it's a Hilbert module. If you want to push it further, instead of, for example, a Hilbert A module Iperb, you can consider this one if you're more interested in C-star algebras. So go and consider, so the module operations are given by Toeplitz operator. Go and consider this, the CSR algebra generated by all Toeplitz operator and also the compact operators. So this is my notation for it. So this is a Toeplitz, so I'm going to call it Toeplitz CSR algebras. So this is another analytic apparatus that you can use. And okay, the idea is to extract geometrical information related to the variety defined by I from your knowledge of operator theory and non-commutative geometry. So, right. So the backbone is given by these Arveson.
Oh, wait a minute. Can you return? Yeah. So, oh yes. It's okay. Yeah.
Okay. So that's it. So remember this notation is Iperb. Always Iperb is a Hilbert module over A, right? The module operation is given by Toeplitz operator. I mean, multiplication by polynomials followed by orthogonal projection, and also remember this notation.
Yeah, so basically the set of symbols for Toeplitz operator are just polynomials. Yes, and the ideal enters as a inner orthogonal projection.
Yeah. So this is why, so I'm going to justify this for you, that an operator replacement, why this is a replacement to the classical algebraic geometry. So remember just what I have told you before. I mean, about the Douglas's index problem and conjecture. So the most fundamental conjecture about this construction Iperb is that it is essentially normal, in the sense that the Toeplitz operator commute modulo modulo compact operators. I mean, Toeplitz operator under adjoints, because Toeplitz operator in this situation already commute with themselves. But I'm going to say that the Toeplitz operator also commute with the adjoints of other Toeplitz operators.
Is Arvidsson only for Drury Arvidsson space or
No,
generically?
So Arvidsson conjecture it for the Rory Arvidsson space, but then Douglas said that it's okay if you use Bergman spaces over strongly pseudo-convex domains. Right. But for weakly pseudo-convex Bergman spaces over weakly pseudo-convex domains, I have told you that no, it's not true in general. For example, for the bi-dis, it's not okay. It's not true. Okay. So this is the Arvidsson's conjecture, and if this conjecture is true, then you have something. You have a short exact sequence of CSR algebras, right? Because the maximal ideal space of your Toeplitz operator modulo compact operator is given by the variety defined by I intersected with the unit sphere. And this is, by the way, one way to extract geometrical information. So I only started with my ideal, and then, right, so made some Toeplitz operator, modified out by compact operators, and then took the essential Taylor spectrum or maximal ideal space, right, some operator theory notions, and that brought me this one. So this is one way to extract geometric information from this operator theory construction. But anyway, right. So the Arvidsson's conjecture tells you that this CSR algebra is commutative, right? And the essential spectrum is given by this intersection. So you have this short exact sequence of CSR algebras by the Gelfand-Neumark theorem. Or if you like,
yeah, question. So this intersection would be essential, would be the space of maximal ideal, this quotient algebra.
Right.
And how generically this intersection corresponds to the boundary of the unit ball.
To this intersection,
so
right?
Which part of the unit ball it might be?
No, the boundary of a unit ball.
Yeah, I understand, but so the question is this intersection. Which part of the boundary it can take?
Oh, so you mean so I have an intersection of my...
Yeah. How this intersection corresponds to the whole boundary?
To the whole boundary?
Yes. So what is this some subvarieties of which dimension or lines or whatever, or complete boundary?
So I don't get your question. So I have a CSR algebra. So it makes sense of talk about the maximal ideal space, right?
Yes. No. Yeah, well, yes. It's completely clear written that your maximal ideal space can be identified with this xi, which is intersection variety with the boundary of the unit ball.
Right.
Yes. My question is how this intersection looks like. Which part of the boundary it represents?
So it might be very complicated. So I'm going to show you that. Okay, this construction is very much interesting.
Yes.
So it appeared like in the 19th century in the work of topologists. So it turns out, so every plane knot you can make by this construction. So these are pretty much, so a lot of smooth manifolds you can make with this construction. I mean, they can be pretty much rich as far as topology and differential geometry goes.
I'm sorry.
But all the time it should be some smooth submanifold.
Yeah. If the intersection is transversal, right. But in some cases, it's not even transversal. But if it's transversal, so that is, the most general thing that you can say is that it is some algebraic variety. Okay. But besides that, it can be, so that is what this talk is about. So, right, it can be very much interesting. So I'm going to show you that. So all exotic spheres you can make with this construction.
Okay.
I'm sorry, some simple examples for the ideal generated by Z1. We obtain just one circle, right?
Yeah. Okay. So you had a question?
Is it correct for the ideal generated by Z1?
Right. For example, ideal generated by Z1 intersect. Yeah. Okay. Yes, that's right.
Okay.
So, right. I'm going to give you examples soon.
Okay.
Right. So, but if this conjecture is true, then you get a short exact sequence, right? Like this, or, right. You get a representation of the continuous, the C-star algebra of continuous function on this intersection over the Calkin algebra, and that is an element of K1, the odd K-homology group of Brown, Douglas, and Fillmore. And okay, Douglas's problem is to identify this one, and his conjecture was that in the specific geometric situation, if everything is nice, if the ideal I is not like a non-radical ideal, if the ideal I is radical and it is a vanishing ideal of an algebraic variety V, which intersects the boundary of the unit ball transversally, then this representation, this C-star algebra representation that I've given you, right, it gives an element of K1, and the Douglas's conjecture tells you that it is exactly given by another famous element in K1, which is given by projection onto the positive side of the spectrum of the spin-Dirac operator. Okay, but my advisor Tang, together with Douglas and Liang several years ago, they proved that this conjecture of Douglas is true if V is a complete intersection. Okay, so by this slide, I just wanted to convince you more or less that, okay, there are some, you can extract some geometrical information from this construction over here. So to follow my talk from now on, just remember this idea over here, that this is a reasonable idea. This is a reasonable expectation to have, that just by studying Toeplitz operator given by compressed shifts, compressed multiplications by polynomials, you can extract some geometrical information. Okay. So now in this talk, this is what we are going to do. We are going to apply this idea of Iperb. So Iperb is a multivariable operator theory way to study the variety defined by I intersected by, let's say, unit ball, by the boundary of the unit ball. So we are going to apply it to a specific situation in differential topology, and this is the construction of exotic. So I need to remind you of two facts, two beautiful things in singularity theory, but discovered by more or less by Milners, John Milners, and this German guy, Briscoe. So let's do that. So I'm gonna like 10 minutes on this background about differential singularity theory. So Milners and Kerver, right? They proved that they are exactly 28 oriented a smooth structure on this topological 7-dimensional sphere. So two of them are standard, the other one are exotic. They're called exotic. So right before Milners, people were more or less assuming that there is only one smooth structure on the, for example, spheres. But Milners, for example, first discovered that on the 7-dimensional sphere, there are some exotic smooth structure. I mean, there are smooth manifolds whose smooth structure is not diffeomorphic to the usual one.
Mm-hmm.
So they are called exotic. And okay, several years later, using some technology he developed with Kerver, they counted those. They said they discovered that they are exactly 28 oriented smooth structure on the 7-dimensional spheres. So there are,
wait a minute. Two standard. One standard is obvious. What is second standard?
The other one is just reverse the orientation of.
Okay.
A smooth structure is the same, but okay, for some reason oriented, right? The orientation is the reverse, but a smooth. So that's why I'm saying that two is standard.
Mm-hmm.
Two is standard, smooth is standard. The rest are called exotic sphere because they were not imagined before the work of Milners.
Mm-hmm.
Okay, there are, if you just Google the term exotic spheres, there are several constructions using Lie theory, whatever, or the way originally used by Milners using quaternions. But okay, if you're interested in an algebraic geometry way to construct exotic spheres, that was discovered by this guy, Briscoe, a German mathematician. He was a student of Herzebruch working on singularity theory. So that is a very interesting statement. So if J, let the index J be an integer from 1 to 28. And then consider this polynomial.
Mm-hmm.
A polynomial in 5 variables, this strange polynomial in 5 variables. So let epsilon be a small enough positive number. Go and intersect the variety defined by this guy. The variety, I mean the set of points in C5 which are zeros of these polynomials, right? Go and intersect it with a sufficiently small sphere of radius epsilon around the origin. So what do you get? So this is your intersection. I am going to denote it by Kj, or some people denote it by Lj. This is called the Milners link. Milners link. So the intersection of this polynomial with the sufficiently small sphere around the origin. So let's dimension count for this one. So our whole space is C5, right? So it is of real dimension 10. So this VFI is of real codimension 2, right? This guy is of real codimension 2. This guy is of real codimension 1. So the intersection is of real codimension 3. So you're inside a 10-dimensional space. So the intersection is a 7-dimensional object, right? So if epsilon is sufficiently small, then this intersection is going to be transversal. So it's a smooth manifold. But okay, Briscoe proved that this is homeomorphic to 7-dimensional sphere. Okay, but okay.
And this is the least of all smooth structures.
What?
This is the least of all smooth structure of 7-dimensional sphere.
Yeah, exactly. So this was known before Briscoe, that the intersection is a homeomorphic to S7. But what Briscoe discovered is that together with the naturally induced orientation and a smooth structure that this intersection gets from your ambient space. So you have your ambient space C5, right? And you have an intersection here. So you get an induced orientation and a smooth structure from C5. And Briscoe proved that. So you have 28 polynomials, right? So you have 28 intersections corresponding ranges from 1 to 28, and Briscoe tell you that it gives you all the 28 oriented smooth structure that was counted by Kerver and Milners. So
and this construction is specific for 7-dimensional sphere or extends to other dimensions?
No, I have chosen this one because this is very much beautiful, but okay. So he has developed a theory. So this Briscoe, he has developed a theory, so you can follow his theory. So, right, and also Herzebroch gave some Bourbaki talks. So, right, no, not specific about 7-dimensional sphere. Right.
I have a
right.
So, does this mean that there are exactly 14 smooth structures without orienting? Of the diffeomorphism?
Yeah. If you don't care about orientation, just 14. So this is an algebraic geometry way, right? To construct the exotic sphere, you go and intersect the zero variety defined by a polynomial with the boundary of the a small sphere, a small ball around the origin. Okay. So Douglas, this was a problem that Ronald Douglas has thought about for a long time. He wanted to find a operator theory way to distinguish among exotic spheres. So definitely differential geometers, so Briscoe, so Milners has discovered, has attributed an invariant called Milners number, mu, to tell apart these 28 structures. But okay, Douglas wanted to find an operator theory invariant capable of detecting exotic spheres. But I'm going to tell you that, so that is one of his motivations to study these Douglas in this problem. And I'm going to tell you that the Douglas-Tang theorem that I have mentioned before, I mean this theorem over here, this K theory, this K theorem here, right, which identifies the Toeplitz extension with the Spin-C-Dirac extension. This theorem is not capable to detect exotic spheres. Why? Because, so you have this intersection over here, right? So if you want to apply the theorem of Douglas, Tang, and Wu to this specific situation, right? If you want to use odd K homology group to detect these K1 up to 28, so what do you need to do? So you need to consider, right? You need to consider the principal ideal generated by Fj, right? And then consider that perp, right? Orthogonal projection of that ideal as a Hilbert A module. And then study its odd K homology group. But okay, the Douglas-Tang theorem tells you that that extension is given by a spin C Dirac extension. But the bad news here is that, okay, the odd K homology group of every odd dimensional sphere is going to be Z.
Mm-hmm.
So in one sense, there is only one spin C Dirac. There is only one spin C Dirac operator on the 7-dimensional spheres. And by this Douglas-Tang-U theorem, all the Toeplitz extensions are identified with the spin C, with the same spin C Dirac extension, because there is only one spin C, just because of topological reason, just because the second cohomology of spheres vanish, just because of that topological fact. There is only one spin C Dirac structure, and this theorem of Douglas-Tang-U identifies all the Toeplitz extension by the spin C Dirac extension. So all these 28. So if you just insist on K theory, right, to distinguish among exotic spheres, okay, you get nothing. All those 28 constructions, they are given the same integer. I mean, the generator 1 or -1 in this group. So you need to find another way to distinguish exotic spheres. So, and now I'm going to tell you about the first. Right. So differential topologies have a lot of ways to distinguish among exotic spheres. So the most famous of them is called Milners monodromy map in singularity theory. So I'm going to, in a quick, like 5 minutes or like 10 minutes, let me see. So I'm going to put 10 minutes to give you an overview of this Milners monodromy map in the usual classical differential topology. And then we try to construct an analog non-operator theory analog of that. So with the hope to find an operator theory way to distinguish among exotic spheres. Okay, so let's do this. So here is the setting. So I'm going to consider a polynomial f. So I'm going to consider a polynomial f. It passes through the origin. I mean, its hypersurface is variety defined by f, passes through the origin, and the origin is an isolated singularity of f. So the most important example we have in mind is Berescom polynomials. So each of these polynomials have this property. Each of these polynomials, the hypersurface defined by them, passes through the origin, and the origin is an isolated singularity. So, but I am going to give you the construction of Milners monodromy map for this general situation. Okay, so Milners' fundamental idea is this one. So the Milners construction of exotic sphere is given by this one, right? You consider a very specific polynomial, right? Consider a zero set and intersected with a small unit, with a small sphere, right, of radius epsilon. So this K, this intersection, this Milners link gives you all exotic spheres if this polynomial f ranges over Berescom polynomials. So the Milners idea was this, because okay, if you study this Milners work, many of his discoveries is about putting what previous classical differential topologies, I mean, he put many of the discoveries of the topologies or differential topologies before him in the language of vector bundles. So in this, so he did this in this. So this construction, this intersection was studied before Milners, but Milners came along and discovered the missing parts. He said that if you want to study this K intersection, go and study these families of perturbations of K. I mean, consider not only the variety defined by F, but the variety defined by F minus C. C is a very small complex number which turns around the origin, intersected with the ball of radius epsilon, and then consider these families of perturbations. So that gives that. So he put these families of intersections into a fiber bundle above the sphere. So that is what he discovered. So that is called the Milners vibration map. So again, as usual, this F is this specific. So think of F as the Berescom polynomial, and then consider this map from the sphere of radius epsilon around the origin, subtract K from it, K is this link, and then map it by the normalization map, the map which sends a point Z, right, to the f of Z divided by the norm of f of Z as a complex number. So Milners proved that this is a fiber bundle. This is a vector bundle. Oh, fiber bundle. Sorry. So this is a smooth fiber bundle. So I'm going to give you a picture soon. But okay, let's first state what he discovered. So just if it is too much, okay, if I'm giving too much detail, so this is the fundamental idea that you have in mind. So for studying of exotic sphere, this is the intersection that you need to study. To study these ones, okay, go and consider these families of intersections. So Milners put these families into a smooth fiber bundle, and this is the formula for it. The fibers I'm going to denote by f of t. Right, so I'm going to point, so e to the power of it, where t ranges from 0 to pi, right, is a parameterization of S1. So the fiber of these, smooth fiber bundle, I am going to denote it by f of t. So how to study k using these families of f of t? So this is the picture you need to have in mind. So intuitively, this is like an open book. Intuitively, the fibers f of t embrace k the same way as the pages of an open book embrace the spine. So k looks like a knot. So you can think of k as a knot, right? And then f of t, your families of fibers, f of t is like the pages of an open book, and k is the spine. So this is the 0, f minus 1. The inverse image of 0 is the 0 variety defined by f, right? And this is your sphere, and k is the intersection of the variety defined by f, intersection with s epsilon. So in this special degenerate case, so k is just a union of 2 points on the sphere. And then f inverse of c is just this one, f of t. So k, so this is the intuition you need to have in mind. So I'm going to use a notation here. So this is called the Milners vibration, right? This is a fiber bundle over S1, a smooth fiber bundle. F of t, I'm going to denote its fiber. Then, okay, whenever you have a fiber bundle, you can make sense of homotopy lift, right? So when t ranges from 0 to 2 pi, you are going to turn around S1 once, right? And you have a fiber bundle, right? So go and just go and turn around the origin, right? Go and turn around origin on this unit circle once, and then inverse image over this fiber bundle, right? So you get a homotopy lifting map, a homeomorphism, right? Which sends you from your fiber at time 0 to fiber at time t. So this is called the Milners monodromy map. So Milners was algebraic topologist. So he also considered, so what is the dimension of f of t? So your space is Cm of complex dimension m, and this f of t is of codimension 1. So the dimension of f of t is like m minus 1. So the most important part of the information of this monodromy map, h of t, is in the middle homology level. So the dimension of f of t is m minus 1. So this homeomorphism induces a isomorphism at the level of let's say vector spaces at the middle cohomology level. So this is also called Milners monodromy map. Also the h of t and its image and the map it induces on the middle homology level, they are called Milners monodromy map. And okay, so I told you that so Milners developed this stuff to find an invariant to tell apart between exotic spheres. And here, so I'm going to tell you what is his invariant. His invariant is called Milners number mu. And this is what? So Milners proved that f of t, the fiber of this fiber bundle, is homomorphic to a bucket of m minus 1 dimensional sphere. The number of these spheres is called the Milners, is called the Betty number.
Why the middle cohomology, or why middle Betty number? Where does middle come from here?
Middle, where does middle come from? Okay, so if you have the answer, so you can guess where does it come from, because f of t,
m minus 1 and 2m minus 2. Okay.
No. The real dimension of f of t is 2m minus 2, so middle cohomology is like, right. Right. Okay. Let me tell you. So in the case of Briscoe varieties, right? In the case of Briscoe varieties, this intersection Milners link Kj, right, represents all exotic spheres, and I am going to tell you that the Milners number mu is given by this number over here, 12j minus 4, and j ranges from 1 to 28. So this Milners number, all of them are different, so they tail apart among exotic spheres. So Milners number mu, right, which is a number of bucket of circles, bucket of spheres, right, which the fiber is homeomorphic to, is an invariant that tells apart exotic spheres. So we want to find a non-commutative geometry way to follow Milners map. So we want to find a non-commutative way to imitate the Milners monodromy map. And the fundamental idea is again here. Each fiber is diffeomorphic to this one. So we are going to find a non-commutative geometry way. I mean, we are going to make an analog of this one using Toeplitz operator. So if you do that, so there is a hope that by studying this one using Toeplitz operator, we can also find a way to tell apart exotic spheres. And okay, Milner wrote a book. Milner wrote a book about this stuff. His book is called Singularities of Complex Hypersurfaces. So it's a small booklet. He develops all the stuff for you in full details. He gives you he and also Vladimir Arnold found some other interpretation of this mu. Okay. Right. But for the special case, so let me tell you just this one. For the special case of Briscoe polynomials, so this is a general form of Briscoe polynomials, right? For the special case of Briscoe polynomial, this number mu, so again, this mu is the number of spheres such that f of t is homeomorphic to. So this number mu for the case of Briscoe polynomials is given by this product. So, great. So for our specific polynomials, right, for this polynomial, if you want to find the Milners number mu, go and subtract 1 from all of this exponent. You get 1, 1, 1, 2, and 6j minus 2, and multiply them. So you get 2 times 6j minus 2. So 12j minus 4. So and that tells apart our exotic spheres. So, okay, but just forget about everything. Just remember, right, Iperb as a Hilbert A module, right? I told you in the first part, and the second thing is this idea of Milner. So now I'm gonna give you my construction, the construction that we had in mind in non-commutative geometry to find a non-commutative analog of Milner's monodromy map, and this is our suggestion. So again, assume that you have a polynomial f which passes through the origin, and the origin is an isolated. So the origin is an isolated critical point of f. For example, every Briscoe polynomial you like. So go and consider this one. So again, so we are gonna imitate this one. So this is our fundamental idea. This is our fundamental idea. So what we are gonna do. So we have our Briscoe polynomial. We are gonna subtract a very small number, right, from it, a small complex number from it, and that complex number we want to turn around the origin once, right? And then we are going to put it back. Consider the variety defined by it and intersect it with the unit ball. We are going to make sense of this. Okay. So this is our suggestion. So this is so consider your Briscoe polynomial, and then consider the ideal, the principal ideal generated by f subtracted from a very small positive number epsilon multiplied by e to the power of it. And then, okay, go and consider this one. Choose your favorite Hilbert space of analytic functions. So I have chosen this de Rorey-Arveson space, and consider the orthogonal projection onto Iperb. So you have a family of principal ideals, right? So you have a family of principal ideals. So PT is a family of orthogonal projections. So here you have a families of Hilbert spaces, and and then assemble all them together. So by capital P, I am gonna denote the assembly of all these orthogonal projections. And by little p, so little p denotes the assembly of all Hilbert A modules over S1, right? Iperb, so Iperb is a Hilbert A module, right? And when T ranges from 0 to pi, you get a one parameter family of Hilbert spaces above S1. So I'm going to put them over S1 or over R. It doesn't matter. So this is my notation. So capital P is the assembly of your orthogonal projection. Little p is the assembly of your Hilbert modules. So this is your total space. So this is your total space. Okay, my first conjecture is that, so based on the computation that we have made, so let me see how much time. Okay, 15 minutes. So our first conjecture based on the computations that we have did is that P is a smooth Hilbert bundle. So it's a collection of Hilbert modules, Iperb, and we prove that it varies smoothly with respect to T. So that is what we check for all Bereskin polynomials. We have checked this conjecture for all Bereskin polynomials. Okay. The next thing, okay. So now you have a smooth Hilbert bundle, right? You have a smooth Hilbert bundle over R. So
wait a minute. Just understand. This is conjecture checked for this specific polynomial. For all others, is not known.
No, I don't know. No, I have no idea. I guess that is correct, right? This conjecture, I guess that is correct. But I am going to make two other conjectures. So for those conjectures, I don't even know where those conjectures are correct for all Bereskin polynomials. But for the totality of all Bereskin polynomials, a smoothness is okay. The conjecture one is just about the smoothness. So that one is okay. So you have a smooth Hilbert bundle, right? So it's a smooth sections denoted by this one. So this is a standard notation. I mean, smooth sections, I mean, the maps, right, can see in the other direction from R to curly Iperb such that PO, that map is identity. Okay. So now, okay, so you have an extra piece of information. You are naturally given, God given another piece of information here. And what is that? Because, so you don't have only a Hilbert module, but you have only a natural connection on it. So what is this connection? So just think how in undergraduate courses in differential geometry, right? In the last chapter, maybe, so they tell you how the Levi-Civita connection is constructed for a hypersurface, a smooth hypersurface in R3. For a two-dimensional smooth surface, right, inside R3, right? In R3, you have Euclidean structure, Euclidean metric, right? But by using orthogonal projection, you can define a Levi-Civita connection, right? A metric Riemannian connection on every smooth hypersurface in R3, right? So go and exactly imitate that process. So what is that process? The process of construction of Levi-Civita connection. Okay, it tells you if you want to make sense of covariant derivatives on a smooth hypersurface, go and do the computation in R3 in the ambient space, and then orthogonally project onto your hypersurface. That's what we're going to do. So let smooth sections of my Hilbert bundle, I am going to denote let's by Kc, right? So it makes sense of take derivative of Kc, right? Because Kc is just a function of time, t, your parameter t, which ranges from 0 to pi. I mean, this is the usual derivative of Kc. So do this usual derivative, and then orthogonal project onto Iperb. So that this guy has this property. Why? Exactly because of I mean the same proof in the differential undergraduate differential geometry book works. Exactly because of that reason, this map, the capital D, I am going to call it a connection, Levi-Civita connection, or if you like, a covariant derivative. So it has the Leibniz property. So it has Leibniz properties, so you can make sense of, okay, look how the apparatus ideas of differential geometry work. So you have a covariant derivative, you can make sense of flat sections. The flat sections are those cases, those smooth sections such that this value is always 0 for them. In other words, those sections Kc, those sections are your smooth fiber bundle, which always live in Iperb. So they are called flat sections. So whenever you have flat sections, you can make sense of holonomy, right? You can make sense of parallel transport and holonomy. So the conjecture 2 is about, because we want to imitate the construction of differential geometry, so that is our second conjecture. So our second conjecture is that the parallel transport map, which sends the initial value of a flat section to its time t value. So the second conjecture tells you that this equation here is solvable. It has solution for every t.
Mm-hmm.
So as soon as this conjecture is true, so I'm going to tell you about some toy models about this conjecture. But if this conjecture is true, then you can make sense of holonomy map. The holonomy map, so I have denoted by u of t. So this is a map from I0 perp to IT perp. It's do what? It considers a flat section, Kc, right? And it sends its value at time 0 to its value at time t. So this is a holonomy map. And because everything is natural, and because of these Leibniz properties, so it turns out to be a unitary map. That is our extra piece of information. Remember, so we wanted to, so we had these exotic spheres. So I told you that from the odd K homology point of view, if you just insist on the Toeplitz operators, you cannot tell apart these exotic spheres. But here is an extra piece of information. Just think geometrically, right? So you have not only Toeplitz operators given by orthogonal project after multiplication. So you have not only Toeplitz operator, but you naturally, because of this connection, you have a unitary map. So our hope is that if you study the interaction of this unitary map, which comes from the connection, Levi-Civita connection, if you study the interaction of this unitary map with your Toeplitz operators, that gives you a way to tell apart exotic spheres. So that is our second conjecture here. Our second conjecture is that we are most interested when the value of t is 2 pi. I mean, when you turn around this unit circle once. So ut, so you have I0 perp, right? On I0 perp, you have Toeplitz operator, and you also have a unitary map. Right? And then this is our third conjecture. Our third conjecture is that this unitary map acts by conjugation of the Toeplitz algebra in this following sense. So if as soon as the conjecture 3 is true, so I'm not telling about that, but if this conjecture is true, then you get the induced map on the K homology level. Okay, but let's forget about that. Okay, but this is our third conjecture, and then this is my last slide. In the last slide, I am going to tell you what, so these are three like bold conjectures. So in the last slide, I am going to tell you what we have done to support this conjecture. So first of all, so we had three conjectures, right? The conjecture 1 about the smoothness, the conjecture 2 is about the transport equation. The parallel transport equation is always solvable at every time t, or at least from the time from 0 to 2 pi. So the conjecture 1 about the smoothness, the conjecture 2 about the solvability of the transport equation. The conjecture 3 is about the conjugation of the unitary map with the Toeplitz algebra. So the conjecture 1 we have checked for all Toeplitz, for Briscoe varieties. All the other conjectures, so we have only been able to prove for very special cases, for example, z1 to the power of k. The next level is z1 to the power of 2 plus z2 to the power of 2. And okay, if you solve that one, I mean, all the complexity of proving conjecture 2 and conjecture 3 for the generality of Briscoe polynomials already exists in the special case z1 squared plus z2 squared. Z1 squared plus Z2 squared. If you figure out to prove or disprove conjecture 2 and 3 for Z1 squared plus Z2 squared, you can figure out what is the picture for the general Briscoe polynomials. In the special case of 0 to the right, I have 8 minutes. For this very special polynomial, right, Z1 to the power of k. Okay, I told you about this conjugation. U acts by conjugation of Toeplitz algebra, but here is what our computation shows. If you, in a very special case, when f is just power of some coordinate function, then you have these formulas.
What is capital F here?
What?
Capital F on the second line.
Capital F is this one.
Ah, yeah.
Epsilon was your parameter.
Yeah. Great.
Right. So what about it? So this conjecture 3 tells you that U acts by conjugation of Toeplitz algebra in this very special case. So we have been able to say more. I mean, the conjugation of U by the Toeplitz operator. So T1 and T2 are just multiplication by Z1 and Z2. Z1 and Z2. So you see that some phase. So that is what we hope. We had the hope to find an invariant studying these phase shifts. So these are very specific phase shifts. And we wanted to, how should I say, study this phase shift and tell apart these exotic spheres. But just by studying this very special case, okay, you cannot say anything meaningful. Okay. That is what all I have wanted to tell you. In more toy models, for example, Z1, Z2, or even for Z1 to the power of K, Z2 to the power of L, as a 2-variable polynomial, you are able to prove all these conjectures and also check. I mean, you can find explicit formula for these phase shifts. For example, okay, that was complicated. I have brought just the one for Z1 and Z2. I mean, our hope is to, so I have not been able to simplify the computations for Z1 squared plus Z2 squared to draw something meaningful from these computations, right? So what we have done, what I have talked to you about this construction, our suggestion for a non-commutative analog of Milners monodromy map, and also these very, very specific computations here. So we have published in a paper. So it's going to be, it was accepted for this journal of non-commutative geometry. So it's going to be published soon. And we hope that, okay, some other guys get interested and do something, and we are also going to think on that direction. Let's see what happens. So thank you very much, guys, for your attention.
Okay, thank you. Questions, please, comments?
I have some question. And so you said that to have a more general formula, you need to do these computations for C1 squared plus C2 squared. Well, I understand that this should be kind of complicated, but you have it for C1 times C2 in this 0.4. Have you done it for C1 times C2? Is that true?
No, I am doing it in C2, in C times C. So I am
because in this 0.4.
Right. So
in this 0.4, in this slide, you claim something about C1 times C2. So do you have the needed computation for that polynomial?
Yeah, I have computation for Z1 squared plus Z2 squared, but that's pretty much complicated. Okay, the construction just shows you that the computations. So what you can infer is that you can prove conjecture 1, a smoothness from it, because you have a specific. So you can write down a specific orthonormal basis for your Hilbert bundle, and that just because you have some specific formula, you can check a smoothness assumptions for it. But okay. But let me tell you, for Z1 to the power of K, right, this monodromy map, this map U, this unitary map is diagonizable. And from that diagonizable map, from the eigenvalues, you can find those phase shifts. But for Z1 squared plus Z2 squared, everything is mixed, and your operator is not diagonizable anymore. And okay, that is something we expected. We didn't expect it to be that much easy, because let's see this one. So Milners computed this one, right? For the Berescom varieties, I told you that this Milners number, right, that is an invariant. And okay, if you go and read Milners' book, so that is a definition of Milners number, right? So there are several definitions as the number of as the rank of the middle homology group, or if you like, as the degree of a map, or there are some algebraic ways to compute it. But okay, in order to compute this invariant mu for the Berescom polynomials, so Milners uses a lot of topological tricks. He uses a lot of topological trees using deformation retracts, and he has long exact sequence of homologies. I mean, he uses a lot of machinery of algebraic topology to come to this specific invariant. So we expect, so far we have not done anything clever. I mean, so my advisor has a beautiful idea for this, constructing this non-commutative analog of Milners map. But besides that, you need some, very, I mean, some clever ideas to compute these phase shifts.
Mm-hmm.
Right.
So am I right that
Now I understand a bit better.
Go on.
Oh, Raul, sorry.
Raul, you want
Correct my question.
Okay.
Am I understand this correct? That the general idea is to associate somehow to this Milner different maps. It's a different smooth structure of the sphere, different unitary operator U. So the collection of list of this unitary operator U will recover your information about this exotic case.
Right. Okay. Right. So that is what you expect from us, because this is the fundamental idea of Milnor. Everything started with this idea over here. I have written in italics, and we have imitated this construction. But from this idea to, I should say, to compute this Milnor's invariant or whatever, so you need a lot of other ideas. The construction is natural, but to extract information from it, you not only need to know differential topology, or you need to have some ideas in operator theory, for example. So you have C-star algebras, right? You have Toeplitz, you have your Toeplitz algebra, right? You can make sense of it as a Hilbert module or a C-star algebra. Then you have an extra piece of information which is this unitary operator U, and there are interactions between this unitary operator and your Toeplitz algebra. Okay, yeah, and great. If you are an operator theorist, so you have this classification theory of C-star algebra. So this operator theory, guys, C-star algebra, guys, has a lot of invariants, right? Okay, that was the idea to use operator. So the fundamental, yeah, you exactly said that. You got the idea. The idea is to use operator theory. I mean. Right, because the people know exotic spheres, right? The differential topology guys already know exotic spheres. They know everything about them. So they have theories, detailed theories to tell you which is which. But we wanted some operator theory way. I mean, invariance that operator theory guys developed to shadow light on these exotic differential topology, right?
And the key point here is this unitary operator.
Yes. So as I told you, if you just insist on Toeplitz operators in the natural setting and the K theory, you get nothing. Because because on the 7-dimensional sphere, just supports one spin C-Dirac operator. So from the K theory, you get nothing. So but if you add the unitary map U to all the Toeplitz operator and study their interaction, okay, that is something.
Yeah.
That might, I'm just saying that might be something, that might be interesting.
More questions or comments?
So these unitary operators U sub T are don't form a one parameter group, right?
They form a one parameter group, but we prove that is not smoothly. I mean, right. Yeah, so far we have only interested in U2 pi. I mean, right, but okay, you might get something new by studying the whole family as one object. But what we have shown is that these families of orthogonal projection P, right? So it's what is the map? So it's a map between Banach spaces, right? It goes from, let's say, R, right? It goes this assembly of orthogonal projections P or U. This is a map from R to the Banach algebra of bounded operators on some Hilbert space. This map is not smooth. That's what we showed.
It's not smooth. And if you turn around from 1 to pi several times, do you expect some monodromy effects?
Yeah. They're not going to smooth. I mean, okay, that might be okay. So okay, that was a bad news from the start because we expected to be a smooth, but okay, yeah, it's not a smooth. That might have very some information. Okay.
Well, so in representation theory, you don't expect it to be smooth in the sense of being smooth for every vector, but you want.
So, say it one more time.
In representation theory, if you have a one parameter group, for instance, or any unitary representation of a group, you don't expect it to be smooth for every vector, just for some dense subspace. And you're saying not even in that sense is it smooth. Is that right? Am I understanding? So, but you say it is nevertheless a one parameter group. So UT applied to US is U sub T plus.
Yeah.
So is it strongly continuous? Is it continuous in the strong operator topology?
Is it? No, we didn't study that. So
Because
just based
that's sort of the fundamental thing for a unitary one parameter group. Because
if
it's strongly continuous, then you have some self-adjoint operator that generates it. So I would be curious if
but if it has semi-group property, it turns out to be a smooth, right? In some sense, right?
But you said it was a group, so you said UT US is UT plus S.
No. Just I have chosen the bad word. So this is just a one parameter family of let's say maps between Banach spaces.
Oh, okay. Sorry, that's what I meant by one parameter.
But not semi-group. No semi-group property. And I'm going to tell you that it is not a smooth. It is not a smooth.
And what do you mean by smooth? In what sense?
Right, a smooth as a map between Banach spaces, right? So as a map between Banach spaces. If you have a map between Banach spaces, you can make sense of the Freche derivative, right? Freche derivative. Right, is that clear, right? So some books on PDEs develop this stuff, for example, Bourbaki, Dieudonné. So right, so you have the differential, so you have undergraduate calculus 3 differential, right? You define differentiability for the maps between Rn and Rm, Euclidean spaces, but you can copy paste the definitions to Banach spaces. So in that sense, I am using a smoothness in that sense.
So it might still be smooth in the sense of there being some dense subspace.
So
operating on that, it's smooth.
Right. So we have proved that, okay. So we have proved something. So it's not smooth in the usual sense of the board. I mean, if everything, if the Banach, if the Hilbert spaces are chosen naturally, but you can change. So we are working with the Rory-Arvesson spaces here. The Rory-Arvesson spaces are just a special, right, elements of a family of other spaces, right? For example, weighted Bergman spaces or Besov-Sobolev spaces, right? So I am telling you that if you understand capital P, your assembly of orthogonal projections, if you change weights, then you can make it a smooth, because that is a fundamental idea of some guy with Beatrice, some PD guy, some several complex variable guy. So his fundamental idea is that you can differentiability and the Bergman weight, right, are two compromising effects. So you can compensate for differentiability using by lowering the weight, Bergman weight. So in a natural setting, it's not smooth, but we don't think that, okay, we have not extracted anything interesting from it, just from curiosity. I told you that, okay, these maps are not gonna smooth in the usual sense of the word, but you can change the weight of Bergman spaces, of your weighted Bergman spaces to make this map smooth, right?
And you said you haven't studied whether it's strongly continuous.
No. So we haven't pushed it, right? Because first we wanted to convince people and ourselves that it is interesting. I mean, our original idea was to extract, find some invariant, some invariant to distinguish among exotic spheres. So that is the first thing we have in mind, right?
Thanks very much. And I'm sorry I misunderstood.
No, that's okay.
Okay, it seems that there are no more questions and comments. So thank you very much again. And let me remind that the next talk will be given by Kehidzu. And then Giovanni. Giovanni, ¿estás aquí?
Sí, estoy. Sí.
Ok, entonces tú sigues después de que Jesús.
Claro, sí.
Okay. Thanks to all. Have a good day and bye-bye.